Good afternoon, everyone, and a happy Women's Day to all the women who are here. And yeah, it's my great pleasure to introduce my colleague and close collaborator, Professor Pani. And as Professor Rao rightly mentioned for Rinty, it is really difficult to summarize his achievements in few minutes, but let me try to do that. So Professor Pani completed his PhD from IIT Kanpur in the year 1986, and he joined the department in 86 itself. He works in the broad area of PDE and numerical analysis. To be specific, he works in the theory and computation of partial integral differential equations, flow through porous media, particularly in oil reservoir studies, viscoelastic fluid flow problems, parabolic free boundary problems, and variational inequalities along with parabolic control problems. So Professor Pani has been an institute chair professor since 2011, and he has been a visiting professor in very reputed international universities and institutes in the past. And about some awards and honors he has received in the past, he is a fellow of National Science Academy of Sciences from Allahabad since 2002, and fellow of the Indian Academy of Sciences, Bangalore, since 2012. So the Indian Society of Industrial and Applied Mathematics have recognized him twice for his outstanding contributions in numerical analysis, PDEs, and industrial maths, once in 2000, and recently he was felicitated and awarded a trophy with a citation by the Home Minister of India. And here in IRCC, he has received the IIT Bombay Best Research Paper Award in the year 2010. And in 2002, he received the C.L. Chandana Award for Distinguished and Outstanding Contributions to Mathematics Research and Teaching. He is in the editorial board of 5 reputed international journals. So Professor Pani has made outstanding contributions to the field of numerical analysis. He has published more than 100 papers and also supervised around 18 PhD students. His research work is very well cited, and he has been very active in both national and international collaborations. So in addition to his excellent contributions to his research in the area of interest, I would like to add that Professor Pani has been working since last many years to promote research in the areas of applied mathematics and scientific computing in India by organizing a lot of outreach programs. So congratulations, and I would like to welcome you to give a talk.
Thank you, Professor Neela, for nice words. Okay. So at the outset, I would like to thank the Institute and the committee members for selecting me for this award. And in mathematics, I will try to keep it in minimal, but let's see how I can achieve it. I will give an overview of the work which I have been, or we have been doing for the last 10, 12 years. So that is the reason why there is a broad title on our tiny joining into computational PDEs. So before we really warm up, so let us see what are the things to come. I talk about enrichment of mathematical research by answering questions posed internally, which are internal to mathematics. So majority of the development happen in this way. And then answering questions posed by external source. So my research will fall under this one. Then for the last 10 to 15 years, or maybe 20 years, I have been working on viscoelastic fluid flow problems. So this is a good opportunity to tell something about what kind of question posed by such model, and how do you translate into mathematical questions. And sometimes we wonder theoretical question like existence, uniqueness, and regularity kind of a result. Why are such mathematical questions relevant to application? I will spend a couple of minutes here. Since the problem which I will be considering, it is an integral perturbation of the Navier-Stokes equation. So, it is pertinent to know what has been done with respect to this problem or with respect to the Navier-Stokes system. And some part of our effort in this direction, I will be also discussing in a layman's language. Then the second part of my talk will be on computational issues, which is very close to my heart. So, we will try to answer some questions posed by the user community. Say for an example, the first question, given an algorithm, how does one believe the numbers crunched by the machine? So, with respect to this problem, I will try to give some answer. So, you can see some strange things like role of linearized problem, role of Stokes-Walter projection, it is a newly defined projection, and some convergence analysis. So, this is mathematical answer to that question. Second question I will pose it at a later stage, and some work in that direction so we have been doing. On conclusion, if time permits, I look back what are other problems we are interested in or our group interested in, and look ahead what are the problems we are currently working on. So, about the enrichment of mathematical research, it is done by answering questions which are posed internally, internal to mathematics. So, for an example, great examples are all Millennium Open problems except Navier-Stokes equation and Yang-Mills conjecture. So, but there is a severe criticism to this approach as it degenerates. Say for an example, if the problem at hand is hard to solve, solve it out of hand. By this what I mean, you just change the problem. This is the kind of degeneracy can happen, and it is happening. The other kind of research is try to answer the questions posed by external source. So, in this case, there is no way you can change the problem, rather you will refine the problem, and then you have to change your tools. And very often our mathematical tools are too ideal to solve such kind of problems. So, therefore, there is a need to develop hybridized tool or new tools to give answer to questions posed by external source. Let us move towards the viscoelastic fluid flow problem. I will start with this quotation. Someone has rightly said, if God has created nature, man has made mathematics to study it. But how does it happen? It happened through modeling, mathematical modeling. So, the next question is, what is a model? Model is an approximate description of the physical reality through mathematical language. Essentially, what you do, you identify the dominant influential factor and try to neglect the less influential factor, then connect them through physical laws, so that you can get a tractable mathematical form and solve it and interpret it with respect to the question you started with the problem you started with. If it does not match, then you repeat the process. Okay. Well, why I have said this? Because what I am going to talk about, there has a relevance on this. So, in mathematics, we only teach tools, various tools. It is like saying we have all the weapons to attack the enemy. Enemy in this case is a real life problem, but wait for the enemy to come, but the enemy never shows up. So, therefore, one has to soil his or her hands to be useful for solving such problems. Okay. So, viscoelastic fluid flow model, let us look at, if you want to consider the motion of an incompressible viscous flow in a bounded domain, it can be described through a set of equations like this. where sigma is going to be stress tensor, U is the velocity, P is the pressure, F is going to be external force, and this is incompressibility condition. Then there are many unknowns than the equations. To make it consistent, then we need some more relationship. Here, some more relationship between the stress tensor and deformation of velocities, and this is known as equation of state or geological relation. So, in fact, it is going to establish the type of fluid you are discussing. So, for an example, sigma is going to 2 mu d. In this case, you will get Newton's Navier-Stokes equation, and it has been a basic model for incompressible viscous flow for the last 150 years. But however, in the mid 20th century, models have been proposed that take into consideration the prehistory of the flow. So, in the morning when you wake up and push your toothpaste, all right, give a force, it will start coming. When you take out the force, it still will come out. So, that is it has some memory in it. So, such problems, the defining relations we will be given through this one in differential form. And then if you rewrite it in and put the sigma in the main equation, you are going to get an integral differential equation, where the kernel beta t minus tau, this is going to be exponential decaying kernel, and this is gamma. When gamma is going to 0, this terms drops out, and this gives away an Navier-Stokes equation. And this is the compressibility condition, incompressibility condition, and initial and boundary conditions are given. So, various numerical, not numerical, experimental observation says after take out the force, the motion does not stop abruptly, it dies down slowly. So, how to translate in mathematical language? It is just saying as limit t tends to infinity, and in some measurement the velocity dies down, t tends to infinity, ut in some measurement is going to be 0. If so, does it die down algebraically or exponentially? If it is that is the case, what rate? These are the questions which bothers the user community. So, since this problem is an integral perturbation of the Navier-Stokes equation, we would first like to know how far the results on theory and computation of Navier-Stokes equation can be carried over this problem. Regarding the Navier-Stokes equation, if you see, the existence of the global existence of a unique solution for 2D Navier-Stokes equation is proved. For 3D is an open problem. This is $1 million open problem. 3D, we don't know whether this problem tells you that prove or disprove the existence of a global solution, unique solution to 3D Navier-Stokes equation. Suppose this is proved, the model is said to be consistent with the mathematics. Otherwise, there is a need to modify the model. That means we are trying to neglect some factors which are not important in 2D, but in 3D they shows up. So, that is how this existential proof helps us. If you disprove it, then there is a need to remodify the model. If you prove it, then it will be consistent with mathematics. That means we have faith on this model. So, in order to put things in proper perspective, we will be talking about some spaces. Don't worry if you don't know this. It is simply saying that the function and its derivative, they are square integrable. And regarding this 0, it says that as if it is vanishing on the boundary. So, such a structure you have, this is a measurement on it or norm, and then divergence free condition can be imposed on this space. So, you will see imposing the divergence free condition has some advantage. So, the weak form of this problem which I stated now can be in this form. What you do, you multiply the function phi, integrate over omega, and throw the derivative from here to here, and the boundary terms is going to be 0. You will end up with this formulation. Now, if you impose this divergence precondition, you can see this condition, this will be 0, that will be free of the pressure. That means we will have an equation with velocity only, which is free of pressure. Once you find u, you can plug it here to find the pressure. Okay. So, what are the results can be discussed with respect to this problem? The first thing I was talking about the decaying property. As t tends to infinity, if the forcing function is going to be 0, then this is going to be decaying exponentially. The next question is with what rate? The rate here is going to be less than the rate in which Navier-Stokes equation dies down. So, this is given through this one. So, when f is 0, this is also decaying exponentially, f is equal to 0. But when f is non-zero and f does not depend on time, and that is what in most dynamical system you do, then it took almost 8 years for us to prove a result like this. I have no time, but I could have told you that a simple trick has helped us to prove this result. Okay. So, existence can be discussed in the same way. Being a numerical analyst, I would like to see the convergence of the numerical solution to the exact solution. For that, I need some regularity result, and very often the regularity result will need some compatibility condition. Say for an example, if you want these guys are going to be bounded, then your data should satisfy this condition. But however, numerous numerical example, computational experiment shows that you don't need to impose this kind of condition on the data. So, the natural question is, without using this kind of compatibility condition, is it possible to prove convergence? So, this is where you started with. So, therefore, you have to be worried about to derive regularity result under heuristically assumed condition in the data without this non-compatibility condition. And also you want to see as t tends to infinity what happens. Okay, so I will skip it. So this paper was written when f is equal to 0, this paper was written in this journal, and I just want to quote just from mathematical review I have taken it. People have, the paper is carefully written and its contents clearly exposed, so that it should constitute an excellent reference for researchers interested in this subject. This is the comment of the reviewer. With my student, when f is non-zero, we have proved some result here. Okay. So, I am talking about the computational issues which is close to my heart. So, let us see what are the questions posed by the user community. So, given an algorithm, how does one believe the numbers crunched by the machine? So, how do you answer this question? This question through convergence analysis, this question can be answered. That means, what is the convergence? You have the approximate solution, you have the numerical solution, and some discretizing parameter tending to 0. You want to show the approximate solution goes to the exact solution. So, with respect to this problem, I will start giving some answer to this. So, if it does, what does it do to user community? It provides confidence that the numbers which have crunched using this algorithm, they are meaningful. The second kind of question is it possible to find a computational solution which is up to some decimal point correct to the exact unknown solution, that too with minimal computational effort? This is in the heart of adaptive adaptive methods, and years to come, this is going to dominate the computational scene. So, in this direction also we have done some work. So, in mathematically, if you want to translate it, given a tolerance means epsilon, a measurement in this case is norm, can it be possible to find an approximate solution UH with minimal computational effort, so that U minus UH or UH will lie in the epsilon neighborhood of the exact unknown solution, and that too with minimal computational effort. So, in order to answer the first question, suppose there are given two finite dimensional spaces having some approximation property. Say for an example, in L2 norm, the approximation property, if you consider this one, should be H square order of convergence. In gradient norm, it should be H, and in the pressure, it should be of order H. And when you do computation, you want to expect that error between exact solution and approximate solution should behave like this. In the same line, you can impose this discrete incompressibility condition. When you impose this discrete incompressibility condition, unfortunately, this one is not going to be a subspace of J1, where J1 you have exactly imposed the incompressibility condition. This is discretely imposed. So, this is not going to be a subspace of that, and this is going to play a role in the error analysis. This is non-conformity will play a role there. So, once you construct a subspace like this, you pose your problem in this finite dimensional setting by requiring that UH for each t is going to be an element of this and satisfying this. Okay. And once you find this one, then you plug it here, and then you can catch pressure approximation to pressure. So, I am not going to detail about this, but I just want to tell you what has been achieved and how it is achieved. So, for the error analysis, you have to compare between exact solution and approximate solution. Unfortunately, direct comparison does not give you what you want. So, therefore, there is a reason to introduce some intermediate solution. You do not compute it. It is analysis, lacuna in the analysis. So, you split this using VH, which is the discrete solution of the linearized problem. So, therefore, this is the effect of linearization, and this is the effect of non-linearity. You dissociate the non-linearity for the linear problem. Then, in order to tackle this, you have to introduce some other tools. Here, we have introduced what is called Stokes-Walter projection and split the error, and ultimately when you put them together, then you can see U minus UH in L2 norm, you got quadratic order of convergence, and P minus PH, P is the pressure and PH is the approximate pressure. So, in this one which is going to be of order H, which is consistent with the approximation property which you have seen. But however, this result is even in the case of Navier-Stokes equation, this is an improvement, because people in Navier-Stokes equation, they get k t to the power minus 1 and h multiplied h, and there are comments by the researcher that they do not know why they are getting t to the power minus 1, it should be 2 to the power minus 1/2. So, you have achieved that. Even in Navier-Stokes equation, this is a new result. This is a new result. So, if you look back some of the work which we have been doing, we have provided a complete solution to an open problem which is cited in this book. When you did this problem, it is a part of my thesis of my student Rajan K. Sinha. That time you did not know that it is an open problem. Then you have also worked on due to presence of integral differential equation. Due to presence of the integral term in time, then there is a demand huge, this demands a huge storage requirement, and that leads to increased computational cost substantially. Therefore, new algorithms are proposed incorporating a sparse quadrature rule to reduce the storage requirement without losing accuracy. And this has been acknowledged by researchers, also is acknowledged in some books, that this is rather a powerful scheme which incorporates a sparse quadrature rule to achieve substantial reduction in memory term. This work was done with Professor Vidarthomi and Lars Wahlben. Then we have proposed some novel tools to analyze the effect of quadrature for integral differential equation with non-smooth data. The second round of problems is concerned with DG methods, discontinuous Galerkin methods. So researchers were struggling to extend DG methods for nonlinear problems. Although there are nonlinear problems they used to do numerical computation, they are struggling to provide some convergence analysis. So this is a thesis from IIT Bombay. With my student Goody, we have extended the analysis for linear problems to nonlinear problems, and then it has opened up the area on nonlinear DG problems. Then with another student of mine, we proved some kind of super convergent discontinuous Galerkin method. You may wonder why discontinuous Galerkin method. I didn't tell you, because discontinuous Galerkin method, like finite volume method, it is going to preserve the conservation properties. So the superconvergence DG methods for nonlinear problem we have extended, and this work was done with my student Sangeeta Yadav and Professor Neela Nataraj. On adaptive finite element method or DG methods, we have done some work related to this, which appeared in IME Journal for Numerical Analysis, so will appear in this, along with Professor Carsten Carstensen and Neela Nataraj. So let us look at earlier results, but my time is up. So earlier we have given a complete answer to an open problem, supporting the open problems cited in one of the proceedings. It is on a single phase Stepan problem. Another kind of work which you have done, introduce a new mixed method which popularly now called H1 mixed Galerkin method, and a lot of Chinese guys are working on it. So we developed such a method, and which is quite competitive to the classical mixed method. We also developed some method called alternate direction implicit method. It will be three-dimensional problem could be solved as one-dimensional problem, where it is going to reduce the computational complexity. So people are struggling to give for evolution equation with positive memory. There are some problems to define ADI method, but we have proposed a new ADI method for such problems with Graham Fairweather, a distinguished visitor to our department, and my collaborator from Thailand, Morakot. So we have written some good papers. These are the outstanding journals, or this is the top ranking journals in numerical analysis. As I said, on adaptive methods we have done some more work, but I didn't present it. So this work has appeared in SIAM Journal for Numerical Analysis, Numeric Math, IM Journal of Numerical Math. There are top ranking journals of numerical analysis. Okay, all right. I will just complete my talk with two results which are direct from the oven. So you are working on finite volume method, finite volume DZ methods for Stokes equation. This is going on with one of my collaborator, Anil Nataraj. And also we have done for subdiffusion problems or super diffusion problems. You have applied finite volume DZ method, which will soon appear in this journal. Recently, we have given a novel energy argument combined with repeated use of integral operator to discuss convergence analysis for fractional evolution problems with non-smooth data. Okay. So lastly, work done with the help of all my PhD students. I have 18. Presently, one is working, so I will have 19 students. And all my collaborators, and I thank all of them for the support, and thank you very much.